The topic today is going to be the Doppler effect. So you probably already know that if a source is moving and it is transmitting a radio wave or actually any other kind of wave, then the frequency of that wave will appear to be shifted for the receiver. If the transmitter is approaching the receiver, then the transmission will appear to be at a higher frequency than it was transmitted. If the receiver is going away from the receiver, so if the transmitter is going away from the receiver, the distance between them is increasing, then the opposite happens. The frequency will be received at a lower frequency than it was transmitted. And so it happens that mostly any signal we receive from space, whether it is Earth orbit or anywhere in the solar system or outside the solar system, has a Doppler effect to it, and also a Doppler drift, which means that the Doppler frequency is changing versus time. So we see that the frequency of the signal is not constant. It varies throughout the observation. And there are many causes to this. One of the main ones, which is always present, is Earth rotation. So Earth rotates around its axis. And when that happens, basically Earth is approaching all the astronomical objects which are rising on the sky, and is receding from the astronomical objects which are setting on the sky. Not Earth itself, but rather the observatory, which is on the surface of the Earth. So we will see some Doppler curve to any object which is in deep space outside the solar system, such as star or a quasar. And the Doppler curve we see depends on the location of the source on the sky. And besides this Earth rotation effect, which is always present, then there are many different kinds of motion in space. So if we have a transmitter which is in orbit, then its own orbit will also give it a velocity with respect to Earth. So that will cause a Doppler, and the Earth is moving around the sun. So that's another cause of Doppler. So today I'm going to share my screen now. We're going to see how we can simulate this Doppler effect or Doppler drift in GNU Radio, and also how to perform some measurements of frequency, which can then be used to analyze the Doppler and obtain some interesting data. The material for today is on the Doppler folder. I just updated this a few minutes ago because I had forgotten to upload one of the files. And the first flow graph we will use today is the drift simulation 1, but I'm going to start from scratch as usual. So I have here my radio flow graph, and what I want to do is to simulate a signal which is drifting in frequency at a constant drift rate. That means that if I plot the frequency versus time of the signal, it will describe a straight line. It will have a slope, and the slope of the line is the Doppler drift, but it will nevertheless be straight. So that's a constant Doppler drift. And it's the most simple kind of Doppler drift you can have. And oftentimes in SETI searches, this is the model that is assumed, because as we will see later on when we compute real Doppler curves from stars, if you don't observe for too long, so if you observe for tens of minutes or even half an hour, you can approximate the real Doppler curve by a straight line, and then you have a constant Doppler drift. So that's the thing we want to do. And this might seem tricky if you don't know how to do it, but once you know what are the tricks, then it's not so tricky to do. So the first thing that I'm going to do is to introduce something which is the signal source. I mean, we've already used the signal source, but only to generate a cosine waveform. There are other options, such as sawtooth wave, and those are really well suited to generating our constant Doppler drift. So we have sawtooth and triangle, and the difference, as we will see, is sawtooth basically goes up and then immediately goes down, whereas the triangle does a triangle up, a triangle down. So let me show this really quickly to show how this looks like. I'm also going to make this a real signal, and I will explain why in a minute, but for the moment, I'm just putting up a plot of this. So that you can see exactly how this works. Okay. So this is a sawtooth wave. It starts at 0 by default. It goes to the amplitude value, which is 1 by default. And when it gets to 1, it backtracks immediately to 0. So this basically happens in one sample. This is the thing we are going to use to simulate Doppler drift. This is going to represent the Doppler frequency increasing over time. And the trick we are going to use is to make the frequency of this, or the period of this, long enough so that it doesn't reach the end before the end of the simulation. So if we pretend that our simulation is only as long as this, then this represents a Doppler drift, which is continuously increasing at the same rate. And there's no backtracking and no weird stuff. Just for completeness, let me show the triangle. So the triangle is similar. The difference is how it backtracks. So this increases linearly at a constant rate. And then when it reaches the amplitude, it decreases at the same rate. And we could also use a triangle since we are only going to use this part of the curve. But I prefer to use the sawtooth because it's more simple to compute basically the numbers we need, because as we can see, the triangle takes half a period to ascend and then another half to descend, whereas the sawtooth takes the full period to ascend and then it descends instantly. So, okay, so far this is simple. We have the sawtooth. And then the thing we want is, this is going to be our Doppler. So the output is going to be the frequency in hertz. And as we saw, this increases. So that's the way we are going to generate a signal, which is increasing at a constant rate. I'm going to put here two variables. The first one is the drift rate, which I'm going to set to 10 hertz per second. I'm going to put here a comment. So this is hertz per second. This is roughly a ballpark figure, except that usually Doppler drift is negative. So for example, Earth rotation Doppler is negative, and other sources of Doppler, such as low Earth orbits, could be positive or negative. The second variable I want to add is the duration of the simulation. So I'm going to stop this at some point. And then I'm going to call this drift duration. So this is going to be 1000 seconds. Basically, I'm going to make this sawtooth wave increase from 0 to whichever number it needs to increase during 1000 seconds. So as long as I keep my simulation shorter or equal in duration to 1000 seconds, then I will not see the sawtooth wave backtracking. So I can just use it as a continuously increasing signal. So how to do this? The drift duration is very easy to apply. So the frequency is 1 over the period. If I want the period to be 1000 seconds, then the frequency should be 1 divided by drift duration. So this is 0.001 hertz, basically, or 1000 seconds period. This means that the sawtooth wave will take very long to increase. And in fact, we can see this right now. So something interesting is that it starts at 0.5 rather than 0. We will fix that in a moment. And if I zoom in, I can see that this is increasing in value slowly. So now it's 0.52, etc. And it will take 500 seconds to reach 1. So I'm not going to wait. Basically, the thing I want to make clear is now we have something that we can use to generate our Doppler frequency or simulation. So the second thing I want to fix is the start. As we saw, the wave was starting at 0.5 rather than 0. And the reason is because of this initial phase and because of how the sawtooth is calculated internally. A phase of 0 corresponds to the midpoint between 0, which would be the offset, and 1, which would be the amplitude. If we want this to begin at 0, we need to go half of the period backwards, because it takes half a period to go from 0 to 0.5. So to go half a period backwards, and we need to do this in radians, one period is 2 pi radians. So half a period is pi radians, and as usual, I need to import numpy. So the only change is here, I'm using initial phase minus pi radians. And now we can see how that looks like. It starts at 0 instead of 0.1, 0.5, sorry, and it increases, and it will take 1000 seconds to reach the top. And I'm not going to wait either. So far, all of this is good and it could serve us, but I want the output of this to be in hertz. So what I need to do is to set the amplitude to the appropriate value, so that the drift rate that I have set here is actually the drift rate that happens in the simulation. And we can think for a moment about what should be the amplitude. So the amplitude is the final value that is achieved. This is going to be increasing from 0 to whatever we set as amplitude. And it's going to take drift duration seconds, or 1000 seconds, to achieve this value. So if the drift rate is 10 hertz per second, then the maximum value it will achieve will be 10 hertz per second multiplied by 1000 seconds, which is 10,000 hertz. So what I'm reasoning here is that the number we need is the drift rate times the drift duration. And probably this is the most tricky thing with this flow graph. So once again, I want to set my maximum frequency at the end of the drift duration. And this would be how long the duration is multiplied by how many hertz per second we increase. So by doing so, we basically will see that now this increases at 10 hertz per second. So one division is 10 hertz. And hopefully you can see that this is increasing at 10 hertz per second. So, okay, we have generated here a signal which has the units of hertz, and it represents the frequency that we want to obtain at each moment in time through the simulation. This is not our final signal, because this is just a ramping signal. It's a real signal. It's not a sinusoid with this frequency. So we need something that uses this as the input frequency and generates a sinusoid, a pure tone, a CW carrier, such as some people say in communications, using this frequency. And the block to do this is a new block, which is called VCO. And there are two options. One is VCO complex. The other one is VCO not complex, so real. And the only difference is the type of the output. So this will generate a complex exponential or complex sinusoid. This will generate a real sinusoid. And we are most of the time using complex signals to represent radio frequency signals. So we will use the VCO complex. And then I'm going to connect it here, and I'm going to pull up the documentation. So the documentation is as follows. It says this is a voltage control oscillator, and the term voltage control oscillator comes because of electronics. Back then and even today, there is an electronics device which is called a VCO, or voltage control oscillator, and it's some kind of oscillator. So on the output, it produces a sinusoid or a square wave or some kind of wave that then we can use in our circuit. And the input is some voltage, and by moving the voltage up and down, we can control the frequency of the oscillator. So that's the way to have a tunable receiver. For example, if you have a receiver in which you need to tune the frequency you're receiving or transmitting at, you have one of these VCOs somewhere in the receiver. So in GNU Radio, we have the same, or rather digital implementation or emulation of this electronic device. And as it says, it produces a sinusoid of frequency based on the amplitude of the input. And then there is a VCO for a real sinusoid signal. The things we need to know are the parameters. So the sampling rate, as usual, is in hertz. And then the sensitivity is the tricky parameter. It specifies how to scale this input signal to achieve the frequency. So the units are radians per second per input unit. And what does input unit mean? Input unit means whatever units we have here, because we don't have any units explicitly here. We have a range of log graph, so that here we have hertz. I believe that's the most simple way to set this up. But you could do as you wanted, and here you could have units of time or any a-dimensional units you decide. So what happens with the sensitivity is the values you have on the input will be multiplied by the sensitivity to yield the frequency in radians per second. And radians per second is not the same as hertz. You need to remember that if you have hertz, to obtain radians per second, you need to multiply by 2 pi, because there are 2 pi radians in one cycle, and hertz means cycles per second. So with that knowledge, what we want is the sample rate is the sample rate. Here, this is okay, and I will probably change this in a second. And then the sensitivity is by what number we need to multiply the input to obtain radians per second. And the input is already in hertz, because we have adjusted the signal source here to have hertz. So if I want to convert hertz in radians per second, then I need to multiply by 2 pi, as I was explaining, because there are 2 pi radians in one cycle. So the sensitivity in this case is 2 pi. But just because the units of the sensitivity are supposed to be radians per second, not because of any other implication. And then the amplitude is the amplitude of the sinusoid wave we are generating. So we can set this as 1 for simplicity. And what else? The sample rate, we can set any number we want. I want to match the flow graph I already have prepared beforehand, so 100 kilohertz. With this, we will have basically 100 kilohertz of bandwidth, which we will not use completely with our frequency sweep, because the maximum frequency that the sweep achieves is 10,000 hertz. So that's good enough. Take care that if you set this drift rate to a high number, for example, if you make it 1000 hertz per second, then by the end of the sweep, the amplitude, which means the maximum frequency, is 1 megahertz, but that doesn't really fit into the sample rate, so you would need to increase the sample rate. Otherwise, you basically get aliasing. So you would see that the frequency retraces to minus 50 kilohertz and then continues increasing, etc. So, okay, 10 hertz per second. What else do I want? I want a frequency sink, because I want to display the frequency spectrum of the signal. And as usual, I want to make this 4096 points. And if I show you this, you will be able to see that the frequency of this signal is increasing slowly, and it is doing so at a rate of 10 hertz per second. We could take some measurements here on the graph and make sure that we haven't made a mistake here in the units or as well. And indeed, this is changing at 10 hertz per second. Something else which can be useful, by the way, I'm going to set this to a larger value, otherwise it basically disappears out of the range of the plot immediately. So something else which is useful is the waterfall sync. So in the waterfall sync, we can see how the frequency is changing versus time. And maybe with this zoom is not so clear, but if we zoom in, we can see that the frequency traces a straight line of constant slope. So this is the thing we wanted to achieve. And the slope is 10 hertz per second. Okay, so any questions about this flow graph? I'm also looking at the chat every now and then in case someone writes a question on the chat. So something else I want to do is to show you how this looks like in Spectrum. We were using in Spectrum the previous week to see some IQ recordings. So we are going to do the same. File sync, then /temp Doppler drift. You can use any folder or file name you prefer. And then I let this run for a few tens of seconds to have enough data to make a good plot in Spectrum. We can see here the amplitude. We could change this, by the way. So if we want here, we can drift frequency, hertz, and the y-axis units is hertz. So if we do this, then rather than amplitude, which is the default label on the axis, we will see frequency. And we will be sure that this is frequency. So now it's currently doing 400 hertz. So something we can check as a sanity check is that the frequency we get here matches the one we get there. So it's about 500 hertz now in both, going to 600 hertz. Because if you use a wrong sensitivity, then you will see that there is a mismatch between the amplitude here, which is the input of the VCO, and the frequency indication here, which is the input of the VCO, and the frequency indication there. So, okay, in Spectrum, how does it look like? I need to specify the rate, which is 100 kilohertz. And then, where is it? Doppler drift. So with this zoom, we cannot see much, but we can increase the FFT size to the maximum. That will give us more resolution on the vertical frequency axis. And then we can see that, yes, the signal is increasing in frequency. We could even take some measurements. By the way, there is the cursor to take measurements. So if you want, you can pull up these cursors and you can select some part of the waterfall. And then, for example, you get the period between the cursors, which is 17.449 seconds in this case. So you could take some time and frequency readings, divide, and make sure that the slope is 10 hertz per second as we wanted. Why do we get these green effects which seem to appear and disappear? This is one of these effects with the FFT. So we have this spectral leakage, and the spectral leakage depends on how the input signal frequency is aligned with the FFT beams. So depending on that relative alignment, we get a different shape for the spectral leakage. And because this is changing FFT bins slowly all the time, we get this periodic effect. That's basically the reason. And in here, we cannot change the FFT window. I don't know what's the window that's been used, but we can, of course, turn up the minimum power to make this disappear if we want. So anyhow, this is really simple, but if any of you is using Turbo SETI, then this can already serve you to generate some test data that you can use with Turbo SETI, because if you want to test Turbo SETI at different drift rates and signal to noise ratios, this is ideal. Probably the only thing you're missing is how to get this output file format into something that Turbo SETI can understand, and maybe we will do that in another session. If not, I did that last year, so you have the materials for that online. And regarding how to generate a known signal to noise ratio, we have already spoken about how to add some noise source here and how to adjust the amplitude there to have some signal to noise ratio in dB per hertz. So in that way, you can really test that Turbo SETI or whatever narrow band drifting signal detection algorithm you are working on is acting correctly as it should be. So, okay, so far so good. This is simple to generate a drift rate which is constant. But in certain situations, we might want to generate a Doppler curve, which is more complicated. Basically, it's not a constant drift rate, so it's actually some real-world curve from some spacecraft or some star or something. So for that, we can also do it. And what I'm going to do is to copy and paste this. So I'm going to save as. Actually, I'm going to start from scratch again. So 100 kilohertz. And test 2. And I'm going to introduce here a Doppler correction block. It's called Doppler correction because it was designed to correct for Doppler. So if you have one of these signals which is moving in frequency because of Doppler, and you know the Doppler curve beforehand, you can correct the Doppler effect so that it stays at a constant frequency. So that was the main goal of this block. But you can use it in the opposite way for Doppler simulation. There's no problem in doing so. So that's what we will do today. And this Doppler correction block is something I did. It's not included in GNU Radio. In the main tree is in GR satellites. So I'm going to paste the link in the Slack channel. Let me do this properly. So this is where GR satellites lives. And where do I have the Slack? Here. There we go. This is an out-of-tree module, so it needs to be installed. If you are using Linux, you can build it from source, but if you have Windows, or even if you have Linux, if you have used Conda to install GNU Radio, for example, Radio Conda, then you can also install GR satellites with Conda. That saves you a lot of trouble. So I believe it's Conda install GNU Radio satellites. It's in the documentation. And if you installed GNU Radio using Radio Conda, you already have GR satellites installed. And the easier way to tell is if you go here and if you have satellites in this menu, then you have GR satellites installed. If you don't, then you need to install it. So, okay, Doppler correction. The way the Doppler correction block works is it uses an input file, which is a time series of Doppler. And it's a very simple text file. We will make one manually as an example. It lists time in seconds or timestamps in seconds and Doppler frequency in hertz. So for example, I'm going to demonstrate how that would look like. I'm opening a text editor. I say at a time offset of 0 seconds, I want the frequency to be 1000 hertz. And I don't even need the dots here or anything which can be read as a float is okay. At 10 seconds, I want the frequency to be minus 7.5, well, minus 7.5 kilohertz. So like this. And at 20 seconds, I want the frequency to be, I don't know, 25,100 hertz, for example. And I could keep going, generate this text file externally, which we will do in a moment, and make this as detailed as I wanted. The resolution could be 1 second, 0.1 second, or everything. The step size doesn't need to be the same. So just to demonstrate that, I'm going to make this at 45 seconds minus 100.5. And then after 45 seconds, it will hold the last frequency. So it will hold minus 100.5. So this is my file. I can go here and say the Doppler file I want to use is this Doppler test file. And the start time is 0. So I will speak in more detail in a second about what is the start time. But since I have this as 0 here, then the start time should be 0 also to match. So I'm going to copy and paste because that's more convenient. And why not also this one? And now we need to think for a second about what should be the input to this Doppler correction block. And to do that, we need to understand again what does the Doppler correction block do. So what the Doppler correction block does is to correct for the Doppler effect of a signal that is following this time series. So imagine we had a signal that is at 1000 hertz at the beginning, then it goes down to minus 7.5, then it goes up, and then it goes down. If we want to correct for this Doppler movement, and we want the signal to end up at 0 hertz constantly all the time, the thing we need to do is at the beginning, we need to move down 1000 hertz in frequency. Then at 10 seconds, we need to be moving up by 7.5 hertz in frequency. Then we need to be moving down. And of course, in between, we need to linearly interpolate these values. So the Doppler correction block is to whatever thing we set on the input, applying this frequency shift, which is basically the opposite of what we have on this plot, on this txt file, sorry. So if I set here a constant signal, which is 1, and the reason I'm making this be 1 is because 1 represents a signal of amplitude 1 and frequency 0. A signal with a frequency of 0 is just a constant. And once I have a constant, the thing I need to choose is the phase, and I don't care so much about the phase. So the phase here is 0, and the amplitude is 1. So I set this as 1, but it could also be minus 1 or any other complex number of amplitude 1. And when I do this, what I can see is that what has happened, I'm missing a throttle block. So if I don't put here a throttle block, then basically everything will happen so quickly that we cannot see it. So this is going from minus 1000 to whatever other value I set at 10 seconds. And then it's going down to minus 25, I think I set. And then it's going up. Probably I don't want to wait because I think the last one is minus 100.5 at 45 seconds. Yet the thing I want to show is that this signal is tracing the opposite of this text file. Maybe I can go again from the beginning. So here I have 1000 hertz, yet this is doing minus 1000 hertz. Now I have minus 7.5, yet this is going to 7.5. And then it goes down to minus 25.1. And here I have 25.1. And the reason is because since this is mainly intended for Doppler correction, it's applying the opposite frequency change from what we have on this text file. If we want to simulate a Doppler frequency, then we have basically two approaches. The first of it is to remember that this will do the opposite of what we write on the file. And then we can simply change the sign of everything when we generate this file. So that will work. It's a simple approach. But then another alternative is to invert the frequency. And maybe that's a good way to demonstrate how to invert the frequency, because I don't think I have showed this before. So there is a complex conjugate. The complex conjugate is the mathematical complex conjugate. So the real part is the same at the output, and the imaginary part, we flip the sign. By doing that, we basically mirror everything in frequency. This is mostly because of how the FFT works, or how complex exponentials represent frequency. So if I do this, you can now see that the frequency has started at 1000. Now it's going down to minus 7.5. And when it reaches minus 7.5, it will go up to 25.1. So that's another way. If you prefer this file to read exactly the frequencies you're generating, you just use the complex conjugate and invert the output frequency. Of course, we can look at this output in Spectrum, and we will see the same thing. So maybe I need to make this smaller, like this. So it's going from 1000 hertz to minus 7.5, then up, then down, etc. And this file could be as complicated as we wanted. By the way, this is a rather precise Doppler correction calculation. So what's going on inside this block is, for each input sample, the frequency corresponding to that input sample is being computed by interpolating linearly over the two corresponding entries on the file. And then once we know that frequency, we change the phase of the signal by whatever phase increment corresponds to that frequency. So basically, the correction here is very, very accurate. The accuracy is set by whatever time resolution you getting here. What else? What's the meaning of the start time? So the start time, basically, it's a way to relate the time axis on this file with the execution of the GNU Radio flow graph. So start time basically means when the first sample arrives into this block, what is the time for that sample, and then it will go to the file and it will look up to whatever time. So to demonstrate that, we can set 15 seconds, for example. And then let me put these together. So if we start at 15 seconds, we would expect the signal to be, I don't know, around 10,000 hertz, maybe going up to 25,000 hertz. And indeed, it starts at 9,000 hertz or something, going up to 20-something thousand hertz. So, okay, so far this only seems a way to start midway in this file. But the reason this is set up like so is that usually when you are doing a real world simulation or even using this for Doppler correction of a real world signal, what you have here is the actual Doppler data for your signal of interest. And rather than starting this at 0, you make these to be timestamps. For the timestamps values, you use the Unix timestamp. So in case you're not familiar with Unix timestamp, is one way of measuring time. And basically it's this number. It measures the number of seconds, not including leap seconds, since the so-called Unix epoch, which is the 1st of January 1970 UTC. So this is how many seconds have elapsed, 16, whatever. So when we generate one of these files, we could make these entries correspond to UTC time in that way using Unix timestamps. And then we can set here the start time. But the best thing is that this also supports several other methods of setting the timestamps. For example, if we are using an SDR receiver, we do not know exactly when we press the play button, so that's the beginning of the data. And there are some SDR receivers. The RTL SDR stick that you have doesn't have this feature, but some more expensive SDRs have some kind of clock, or they can be synchronized to GPS. So in addition to the IQ samples, they will also send the time of the first sample or every 1,000 samples or whatever. So this Doppler correction block will synchronize itself and see that the SDR has a GPS receiver to get time and says that the time corresponding to the first to the first IQ sample is whatever Unix time. So then it will go and start by the point of the file that actually corresponds to the time you are running this. And the file can be much longer. It can start way before when you want to use this and end way afterwards, the end of your simulation or observation. Okay, questions about this? Okay, good. So at the moment we have this Doppler file, which is just a silly example with some random numbers to show you how this works. But we want to make this more realistic. So we want to calculate Doppler effects for real world objects and write Doppler files like this. So I have prepared some scripts. These are in the repository, and you can look at those and you can use those for your own projects. These maybe are also helpful outside of using GNU Radio. So if you need to calculate Doppler for something, then maybe this code is useful. Let's start with the first one, which is this AstroPy Doppler correction. And I guess all of you are, close this, all of you are familiar with the AstroPy Python library. It's a library to compute stuff in astronomy. So we will use this script to compute the Doppler for any object which is far away on the sky, such as star, a quasar, or basically anything outside the solar system. And the Doppler effect that we will compute corresponds to the rotation of Earth and also to the rotation of the Earth around the sun. We will not take into account any other effects, such as the proper motion of the source. If we know the proper motion of the source, and maybe we can look that up with AstroPy also, we can factor that in. But usually it's not so important because the proper motion of the source stays constant for, I don't know, months, years, decades. So it's not going to change throughout the observation. We mostly care about Doppler effects, which change in the matter of seconds, hours, or throughout the year as our Earth rotation or the Earth movement around the sun. So, okay, we have a bunch of command line parameters to specify what we want to do with the script. Basically, we need a carrier frequency. As you know, the Doppler is proportional to the carrier frequency. So if you have a higher frequency, then the Doppler shift will be higher. So we need to specify the carrier frequency. Observatory, which is the name of the observatory. We can use any of the observatories which are known by AstroPi. And then target, which is the target we want to observe, or the target for which we want to compute the Doppler. For the target, we can use either a target name, such as the name of a star. I think I used Vega on one of the examples. Or we can also use right ascension and declination coordinates. We will see how to do that. The start epoch, which is the beginning of the timestamp for the beginning of the Doppler file. And this uses this ISO format. We will see how that looks like in a second. Duration, so how much duration worth of data we want to put into our Doppler file. Of course, this needs to be longer than the simulation or observation that we will do, but it can be much longer. We can make this a week long if we want, and reuse it for all the observations during that week. Time step is the time step in seconds. So we had here the Doppler file. Maybe I should have done this larger. So here the time step is 10 seconds, here not, just to demonstrate that we can use any time step. So we can use the time step. And for these kind of objects, 10 seconds is more than enough. If you have something whose Doppler drift is changing very quickly, then you need a finer resolution, such as 1 second or 0.1 second. But for Earth rotation, 10 seconds is usually fine. Output file is the path of the file we want to write. Then we have the simulation mode. So the simulation mode inverts the sign of the output, and that's used so that you do not need to include the complex conjugate. So rather than including the complex conjugate, it will change the signs of all of the entries, and then you can forget about this thing. We can also add an offset to whatever data we are generating. And why would we want to add an offset? We will see that in a minute. The reason is basically, usually we have a Doppler which is changing throughout the day, which is due to the Earth rotation. And then we have a much larger Doppler, which is due to the Earth rotation around the sun that is pretty much constant throughout the day, and it can be rather large, maybe 0.5 megahertz at X band, so at 8 gigahertz, because, well, the Earth velocity around the sun is quite large. So what happens is that we might want to tune our receiver at a 500 megahertz, at a 500 kilohertz offset, assuming that the Doppler is around 500 kilohertz because of this effect, just to null out most of that Doppler effect. And then we can add that offset to the Doppler file, because we are already accounting for that by tuning at an offset. So we know that our signal is at plus 0.5 megahertz plus some other small quantity, and we decide to already tune up by 0.5 megahertz and take care only about that other small quantity. And we also have a plot parameter to do a plot of the Doppler curve, which is quite useful to check if it has been computed correctly. So how does this work? Basically, this is some simple NumPy code. So if you're used to NumPy, this will not be surprising. I compute an array of times according to the parameters I have specified. Then I try to fetch the target by name. So this chi-cord with a name will fetch the target, but if it doesn't, this chi-cord will, if this looks like a right ascension and declination, will parse it, and we will get a target with the right ascension and declination we have specified. If this fails, then we try to fetch the target by name from the catalog. And if we cannot resolve the catalog name, then we basically raise an exception and complain. So once we have that, we need the location of the observatory that's using the offsite, which basically uses the AstroPy database of observatories. And to compute the velocity, there is this radial velocity correction function, which when you specify the heliocentric correction, computes the velocity which is due to the Earth rotation and to the Earth rotation around the Sun, not to the source proper motion, not to the movement of the Sun through the Milky Way, etc. Just those two movements within the solar system. And so we compute this, we convert it to meters per second. There's a minus sign here, which has to do with the sign convention for this function. Then we convert our carrier frequency from megahertz to hertz. So I forgot to say it, but we are supposed to fill in the carrier frequency megahertz because it's often more convenient. And then the formula for Doppler, I'm not sure if you know this formula, but basically the Doppler effect, at least in the Newtonian approximation, there are some more complicated relativistic formulas which take into account both special relativity effects because of the individual velocity of the source and the receiver. Here we only have the relative velocity between the source and receiver, but if we want to take special relativity into account, we need to factor in the absolute velocities of the receiver and the source with respect to some rest frame, I believe, because absolute velocities and relativity, now that I say it aloud, is a weird notion. Maybe it all cancels out, I don't know. And then there is also a general relativity term because of the gravitational field. So you have this gravitational redshift or blue shift, but we are ignoring all of that. So this most simple Doppler formula is you take this minus sign. So you need to remember that when the object is coming towards us, the Doppler is positive. When the object is moving away from us, the Doppler is negative. So then for the usual convention of velocity, which is the time derivative of distance, you need the minus sign here. So then velocity divided by the speed of light. And this, of course, is dimensional because we are dividing velocity by velocity. And we multiply this by carrier frequency in hertz. So we get Doppler frequency in hertz. And finally, we format everything to the appropriate text file format, inverting the sign of the output if we are running in simulation mode. And we make a plot using matplotlib if we need to make a plot. So that's the script. Let me show you an example of how this works. So I have it here, and let's do AstroPy, Doppler correction, carrier frequency. I'm going to go with 8.4 gigahertz. So that would be 8,400 megahertz. This is a usual frequency for spacecraft. So if you are receiving spacecraft, especially if they are in deep space, they will be around this frequency. The observatory, I'm going to use HCRO, which is the Hat Creek Radio Observatory. That is where the Allen Telescope Array is. For the target, I'm going to use the star Vega, for example. Then we will use some right ascension and declination, if I remember the format. The start epoch, I'm going to make it today. So today is 2023, July 18 and 0000. So this would be UTC. And this is this famous ISO time format. So you have year, month, day, then the letter T, hours, minutes, and perhaps seconds if you want. I think it's not mandatory here. An output file, I'm going to make it viga.txt, and I'm going to make a plot. I also need the duration, so duration. Let me remind myself real quickly how many seconds in a day, 86,400. So this will quickly generate 1 day of Doppler. So if we are trying to receive signals from Vega at 8.4 gigahertz from the Allen Telescope Array, this is how the Doppler will look like throughout the day. And you can see that it's mostly centered at minus 600 kilohertz. So that's what I meant by most of the Doppler in quantity is due to the Earth rotation about the sun, around the sun. What happens is that currently, because of where Vega is in the sky and where the Earth is in its yearly orbit around the sun, the Earth is moving away from Vega. So we have this minus 650 kilohertz. And on top of that, we have this sinusoid because of the Earth rotation. And this will, the phase of the sinusoid will depend on the location of the radio telescope. And then the natural question is, why does this sinusoid appear to be slightly wonky? So we would expect this to go up to the same value. And if we plot more days, so let me remind myself how to multiply, for example, 3 days. If we plot 3 days, now it is apparent that besides this sinusoid, because of Earth rotation, the Doppler is decreasing. And that's because the Earth is moving around its orbit around the sun. So in fact, we have a larger sinusoid with a period of 1 year. And for these 3 days, which we are including in the plot, the larger sinusoid is decreasing, and then it will increase again. So what else can we do with this? We can go back again, and we can decide to add an offset. So if I add an offset of 650,000 hertz or 650 kilohertz, better said, what I get, I think this includes the offset on the plot. What have I done wrong? The offset is in hertz, I think. Yeah. Yeah, I was misreading this. It's only 65 kilohertz. So if I add 65 kilohertz, then the iris is more or less centered at 0. Why could I want to center this at 0? Because we are usually working with signals which are around 0. And then by doing this trick, I don't need a much larger bandwidth. I can just have a bandwidth which the signal fits into, and the maximum frequency here is minus 12.5 kilohertz. So any sample rate which is larger than, I don't know, 25 kilohertz or something will be good enough to simulate a signal which is drifting like this. And what I can do is enable simulation mode. So this flag doesn't affect the plot, but it affects the sign of the output. So we can look at this really quickly. And then you can see that the beginning of the plot was 6,700 hertz, but then this has the minus sign on the output file because of this simulation. And if I go here and remove the complex conjugate, and change my file to make this Vega. Then we see that the frequency is 6,700, and presumably it's moving, but it's moving very slowly. So instead of waiting, what I'm going to do is here on the throttle block, I'm going to multiply this by 100. And by doing this, we achieve a simulation which is 100 times faster than real time. So now we hopefully are able, no, yeah, I've also made a mistake, which is the start time is set to 15 seconds, but we do not want 15 seconds. We either want, let me open this up here. So we either want this number, which is the start of today as Unix timestamp, or we could have some Python code here that computes the current timestamp at when the flow graph is run. So we would have something like a real-time simulation of how the Doppler from Vega currently is. But here I've decided to start at the beginning of the day, and you see that the Doppler is increasing and then it will decrease. And basically it will do the same that it did on the Doppler file. And that's the way to generate the Doppler shift, which is changing in a realistic way. What else? What else? I said I wanted to show how to put in here some coordinates. And I think we can do something like 7 hours, 30 minutes, 49 seconds. I'm inventing this, of course. And then minus 17 degrees, 40 minutes, 12.7 seconds, something. And then it works. I don't know if this is correct, but I guess so. So at different location in the sky, we get a different Doppler curve with minus 30 kilohertz in this case, and the phase of this sinusoid is different. Okay, any questions? As I said, this script uses AstroPy, and it basically relies on the skycord object in AstroPy, which represents a fixed location on the sky. So you can search it on a catalog, but it's basically a constant right ascension and declination. This is good when you are looking at something which is basically outside the solar system. But if you are looking at objects within the solar system, so any planet or asteroid, any spacecraft, then you need to use something else. And there's something else you can use is this Horizon system from NASA. So this is basically a web service in which you can calculate ephemeris for many objects in the solar system. You have spacecraft, you have asteroids, planets, etc. So you could choose a target body here, the observer location. We're also using the Allen Telescope Array, the time. So this is for the beginning of July, and you click Generate Ephemeris, and you get your right ascension and declination. And more importantly, for what we're doing today, you get this delta, which is the relative speed, relative velocity between the object, in this case, a spacecraft, and the radio observatory. And this is in meters per second, I think. The units are somewhere, maybe at the bottom, maybe somewhere here. So delta units, sorry, I was messing this up. Delta is the distance, del dot or delta dot is the velocity, and the units is kilometers per second. But the column you need to look at is del dot. So for example, this object is moving away from Earth at 3.2 2 kilometers per second. This on its own is only partly useful because we want to use these from Python. So luckily there is something called AstroQuery, which is a Python library that can be used to query different online databases. One of them Horizons, but there are also others. So I have these Horizons Doppler correction, and it uses AstroQuery JPL Horizons. And this is quite similar to the previous script, which was using AstroPy. The main difference is instead of using AstroPy, we use these horizons. We indicate here the name of the spacecraft. I have called the spacecraft, but I guess you can also use a planet, and we can test even with a planet now. The location of the observatory, the epochs, so these need to be formatted in Julian days, I think, or something, and then the number of steps. So you get the ephemeris, you have this delta rate, which is what was del dot before. We convert from kilometers, or actually kilometers per second, to meters per second, and we have the same formula, and we have more or less the same code to write the output and the code to plot. So this is very similar. So carrier frequency 8400, and I'm going to go spacecraft Mars just to check if this works. So Mars is a planet, not a spacecraft. Start epoch, the same. Duration, the same, 86400. And output Mars txt simulation mode. Why not? And what's going on? Yeah, apparently Mars is ambiguous, and it wants some non-ambiguous object. I think you can do Mars at 499, or maybe not. Let's see how. I didn't test this with Mars before, so demo effect. Let's see how this works on the. Yeah, maybe I can just go 499. This is somewhat confusing because the objects have IDs, but they also have names. So I'm not sure if 499 will work. If not, there is some easy modification of this script which can fix this. And now I'm realizing that this is maybe a very large query, because I'm doing every 10 seconds for a single day. So remember, AstroPy was doing the, oh, and I have forgot about the plot. So AstroPy was doing the calculations on your machine. This is doing the calculations on a remote machine at JPL and downloading the results. So here it is. This is the Doppler curve for Mars. And in this case, we could have used AstroPy by picking the right ascension and declination that Mars is currently at. There wouldn't be too much of a difference. Of course, we need to change that during the year because Mars' position on the sky is not fixed. But I also want to demonstrate how this can look like for a spacecraft. So I'm going to use actually one of these, the Mars Reconnaissance Orbiter, which is called MRO. This is a spacecraft which is in orbit around Mars, hopefully no. So I think I can use -74, and I probably need an equal sign here because of Python weirdness with parameters that start by minus. So, okay, it seems that it's happy with -74. And then when we get the plot, we will see how this looks like. Okay, so here it is. And this is very different to what we saw before for Mars. Still, we can see there is some kind of sinusoid here. So the average of this thing is sinusoid. And if we compare this plot with the plot for Mars, we will be able to see that, yes, this average sinusoid is the same sinusoid. But then we also get this additional sinusoid, and this is because this spacecraft MRO is in orbit around Mars. So um, it has an orbital period of, I don't know, 1 hour, a couple hours. Apparently, you can just compare the distance here, so 2 hours. And then because of the rotation every 2 hours, we get this additional Doppler effect. And there is no way we would have computed this with AstroPi. We need the trajectory of the spacecraft around Mars. And if we choose any other of the Mars orbiters, we will see that the Doppler curve is different. So either the amplitude is different, or the period is different, or most likely the two of them, because all the spacecraft are in completely different orbits. So if you record some signals from Mars and you are not sure which spacecraft is, one way to identify is to record for a while, for a few hours, and then to try to match the Doppler drift you see on the signal on your observation with the Doppler curves you compute here. So the thing I want to show you now is a technique to measure frequency, or to measure Doppler in this case, which is extremely accurate. The most common way of measuring frequency in radio astronomy is to use a waterfall plot or spectrum data. So you do an FFT, as we have been doing all along, and then you find in which FFT bin your signal is located. And with that knowledge, you identify the frequency of the signal. The disadvantage of doing this is the resolution, because unless you make your FFT really, really large, then the FFT bin space can be 10 hertz or it can be 100 hertz. So even if you find your signal on one specific bin, that will only tell you the frequency with a resolution of maybe 100 hertz if the FFT bin is like so. There are more advanced techniques where you look at the power in 3 adjacent FFT bins, because the signal in general will be straddling between 2 FFT bins. So part of the power will be in one bin, part of the power will be in the next bin. And from comparing those powers, you can sort of try to interpolate in what specific frequency in between those two bins the signal is. Nevertheless, these algorithms are a bit complicated and not too accurate. Of course, in SETI searches, it's common to use a frequency resolution of 1 hertz. So there are very, very large FFTs being done. And in the end, you end up with 1 FFT beam per hertz. And you also need that to achieve a very good sensitivity, as we saw when we simulated narrowband signals of different powers. But there is a completely different way to measure frequency if your signal is narrowband and spectrally pure. So this works for tones. It's very useful for spacecraft signals, any signal which is artificially made and pure, and some techno signature candidates are also like this. So this technique can be used. The method is not so good when the signals fluctuate in power or tend to disappear. In those cases, it is better to fall back on the FFT approach. But nevertheless, this is really accurate because it's based on counting phase rather than frequency. And as you might know, the phase, or actually the frequency, is the time derivative of the phase. So in other words, phase is the integral of frequency, you can think of phase and frequency as space or distance and space or distance and velocity. And they are also related because, as we have seen, velocity induces a Doppler drift, which is a frequency change. A movement or a change in distance induces a phase shift or a change in the phase of the signal. The only problem of phase is that it's ambiguous modulo 2 pi, so you need to count all those phase cycles or those phase wrappings. And if you make a mistake in counting because the signal is not good enough, then you have an error. But if you are able to track the signal well enough to be able to keep track of all the phase wrappings that it does, then this method is very accurate. It's based on something which is called the PLL, and PLL means phase locked loop. It used to be, once again, an electronics circuit which had an input signal and then try to follow the phase of that input signal. And here in GNU Radio, we have something which is digital and is mimicking the operation of that electronic circuit. And if you search here for PLLs, there are actually 3 of them. So depending on what you want to do, one of them might be better than the other one. The one we are using today is called PLL carrier regeneration. So what it does is it locks to the phase of the input signal, which might be noisy because our received signals are usually noisy. And then it generates a very pure, noiseless output signal of the same phase and hence of the same frequency. And what we are going to do is to run a PLL to lock to the signal, and then we will measure the phase of the output signal of the PLL. If we skip the PLL and try to measure the phase of the input signal directly, we'll find that the phase is very, very noisy, and we are not able to get good results with the method. So we do need the PLL. What else? Yeah, as you might have noticed, I'm using, for the sake of time, this Doppler measurement flow graph, which is already on the repository. And what I'm doing here is I'm simulating the Doppler for Vega. So we generated this before I have actually updated the flow graph with the current Vega Doppler file and the timestamp. Then we are generating a rather weak signal. So we are setting a CN0 of 30 dBs per hertz. Remember that this means that the signal is 1,000 times stronger than the noise in 1 hertz, or in other words, the signal is as strong as the noise in 1 kilohertz. So definitely this is not the strongest signal one might encounter. And to do so, we use the Gaussian noise source, as we have done in previous tutorials. And then something else we need to do is we need to shift our signaling frequency, because if we check the Doppler file for Vega, this has minus 7,000 basically. And the minus sign is because of the simulation mode. So again, because of the Doppler correction works in the opposite way. So the signal will start at 7,000, or actually 6,777 hertz. To make the PLL lives easier, we need to have the signal initially as close as 0 as possible. Then the PLL will keep track of the frequency of the signal, and the frequency can drift away from 0, and the PLL will track it. But initially, to achieve lock, to achieve tracking the signal, it is better, because it simplifies the PLL's task, that the signal is as close to 0 as possible. And to do so, we are doing a frequency translation, but I want to do this in an exact way, because a way to achieve this would be to do a signal source, connect it here, this doesn't exist, put here 7,000 hertz, and here you go, this is moving the signal, minus 7,000 hertz. This is moving the signal 7,000 hertz down in frequency. because when we multiply something by an exponential of minus 7,000 hertz, we shift everything down by 7,000 hertz. The problem is every calculation done here, including the frequency, is done with floating point numbers. And floating point numbers are not exact. If we want to measure frequency very precisely, we need to be exact in what we do. And the way to do this is to generate the same kind of 700 kilohertz or minus 700 kilohertz complex exponential, but we generate it in a way which is periodic. So we use this vector source. This will repeat whatever we put here periodically. And what we do is basically we do 100 cycles of this exponential and make it frequency 7 kilohertz so that it's periodic and has the required frequency. This is, if you think about this for a moment, you will realize. So what happens here is this is a sequence of 100 points, and then if I wanted to generate 7 kilohertz, I would need 7 kilohertz divided by the sample rate, which is 100 kilohertz. So this is what I have here. 7,000 divided by 100,000, the thousands cancel out. And since I have a 100 on the denominator and the exponential is 2 pi periodic, I can go up to 100 here and then it repeats. So sample 101 would be exactly the same as sample 1, etc. And that's the way of having something which is exact. This is exactly 7 kilohertz because it's periodic. There is no rounding anywhere. Even if these numbers, so this quotient is not going to be exact, by the way, because it's computed with floating point numbers. But the fact that this is 100 samples long and it does 7 cycles within 100 samples is what makes this be exactly 7 kilohertz. So, okay, so far I think I'm going to disable this. And what I do is I have my Doppler correction, which is simulating the Doppler, the noise source, the vector source to shift this in frequency. And this is the output of the PLL carrier generation, which I'm plotting on the frequency sink. And I'm also plotting the output. What are the parameters that we need to set on the PLL? The first one is called the bandwidth. And the bandwidth basically indicates how fast, this is in hertz, so 10 hertz of bandwidth, indicates how fast the PLL can track changes in the signal. If we set a small bandwidth, then the PLL will be able to cope with weaker signals because in a certain way it's doing more averaging. But on the other hand, if the signal changes too rapidly, the PLL will lose lock, and then this method doesn't work at all. And also, it is harder to initially lock to the signal. If you set a larger bandwidth on the PLL, then the PLL is able to lock faster initially. It's able to track faster changes in the signal. But if the signal is more noisy, then the PLL will lose lock. So you can experiment with different values of the PLL here and see that if you set these too high, maybe 1000 hertz, with 1000 hertz, I can promise that it will not achieve lock. With with 100 hertz, maybe it achieves lock. And if you set the PLL bandwidth to low, 1 hertz, for example, you will see that this has a hard time locking initially unless you refine this and make it 7.8 kilohertz or something. So how does this look like? This blue trace is the initial input signal. Let me do some averaging. So we have the noise and we see that the signal is noisy. And the red is the PLL output. So this is not noisy at all. It's a pure tone. And we see that the PLL is tracking the frequency of the signal. The blue signal is moving in frequency and the red signal is moving together with it. So that's what a PLL does when it's working. To demonstrate when a PLL, by the way, this is, where is it? This is 100 times faster than real time because otherwise we wouldn't see the Doppler drift. So let me, demonstrate setting 1000 Hertz, how a PLL that cannot look like. So this is actually trying to look so hard that all the output is spread in frequency and you see that it cannot do anything properly. Let's try 100 Hertz to see if this is any more reasonable. Yeah, so you can see it's jumping. You can see some tones. Sometimes it locks a little bit to the signal, but then it unlocks and it jumps again. And let me now show 1 Hertz. I believe this won't lock either. Yeah, so this is very slow to move. So it is barely noticing that the signal is below it. And I don't know if it will notice. It seems to want to go down and track the signal, but it's having a hard time. Maybe I try 3 Hertz or something. Yeah, so this is trying to track the signal, and now I think it has achieved locked. We would need to wait for longer to see if the signal moves faster than the PLL can track, and then the PLL loses lock. So let's return this to 10 Hertz. And by the way, if you look at the documentation, the loop bandwidth needs to be in radians per sample. So the way to convert between Hertz and radians per sample is multiply by 2 pi, divide by the sample rate. If you think about the units, this is in cycles per second. This is radians per cycle. This is samples per second. Then some units cancel out, and this works out to be radians per sample, as we wanted. And this is minimum phase per sample, maximum phase per sample. So you can use this to restrict the frequency range that the PLL can cover. As you saw, when the PLL unlocks, it oscillated throughout all the spectrum. Maybe we want to restrict that oscillation to help it lock again. So you can set here another frequency. This is again in radians per sample, and minus pi and plus pi are the maximum frequency. So sample rate divided by 250 kilohertz in this case. So this is the operation of the PLL. If we look at the phase, what we can see, I'm going to stop this now, is that the phase of the signal goes from plus pi to minus pi, and then it wraps around because, as I said, phase is periodic modulo 2 pi. And by counting the unwrapping, so I go here, this is 1 cycle, 2 cycles, 2.5 cycles, 3.25 cycles. By counting like so, I can make an unwrapped phase measurement. And then by measuring the unwrapped phase between 2 moments in time, and remember phase is like distance, so dividing the distance between 2 moments in time by the time elapsed, we get velocity. So in the same way, dividing phase between 2 moments in time by the time elapsed, we get the average frequency between those 2 instants. And this average frequency is very precise because for the PLL to be able to lock, it needs to track the frequency, the phase of the signal fairly accurately. Depending on the signal to noise ratio, fairly accurately might mean a few degrees or up to 10 or 20 degrees, but not more than that. And then if the phase error is just 10 degrees and you integrate for a long time and divide that phase error by 100 seconds or whatever, the frequency error you get is very small. So that's the way to make a very precise frequency measurement. And now this has been running for quite a while, so I'm going to close this. But I'm missing these extra blocks. So what I have here is the phase unwrap block. This is also from GR satellites. This looks at the input and keeps track of the integer number of cycles. It unwraps the phase and counts cycles elapsed, and also the fractional part of the phase. And the output is a 64-bit integer, so that you can count many phase cycles. Otherwise, with a 32-bit integer, you will overflow in some situations, followed by 32-bit floating point number, which indicates the fractional part of the phase. And that's the reason this is purple, because the output is 8 plus 4, 12 bytes. So those numbers, you can treat them as opaque values and look at them later on. What I'm doing is the flow graph runs at 100,000 samples per second. So I only want to generate 10 measurements per second, because otherwise my measurement file will get large pretty quickly. So to take 10 measurements per second, basically I decimate, I keep one in every 10,000 samples. And that's because if I have sample rate, which is 100,000, output rate, which is 10, the quotient is 10,000. I round it just in case this is not an integer. And this block keep one in n says as its name. So the first sample in every block of 10,000 is sent to the output. The rest of them are dropped. And that's the way to decimate and obtain just 10 measurements per second instead of 100,000. And I'm saving the output on a file. Vector length 12 anytime you are using this phase unwrap block, because it's an 8-bit integer, 8-byte integer, sorry, plus a 4-byte floating point number. So let's run this again, and now we are storing these measurements to a file, and we need to run this for some time. Meanwhile, I'm going to show what we do in this Jupyter notebook. So there is the Jupyter notebook in the repository. And what we do is we read the file that we are saving. This is, so we read it as 8-bit integers. We reshape it to have 12 elements per row, because we know that our measurements are 12 bytes. And then the first 8 bytes in each measurement, we can view them as a 64-byte integer, because that's what it's supposed to be. And that's the phase integer part. The fractional part is the last 4, and we need to interpret those as a 32-bit floating point number. And then we can do the combination. So we have the phase integer, and then the phase fractional is in radians. So to get cycles, we need to divide by 2 pi. And this is the phase, just unwrapped phase. I'm going to stop the flow graph now. So as you can see now, this frequency is larger, because this has gone down in frequency due to Doppler drift. So let us stop it to prevent it from generating an output which is too large. And then let's run this, and how does it look like? So if I show you the first phase integer values, you can see -1, -2, -3, -4, -5. This is because the phase is doing at the beginning, so this is before the PLL has locked, approximately 1 cycle for each measurement, and we have 10 measurements per second. So more or less here is doing 1 cycle per second, or 10 cycles per second, or 10 hertz. And at some point the PLL locks, and the frequency now corresponds to the accurate frequency of the signal, and we can see that the change in a tenth of a second is, I don't know, 7 or 8 cycles. And this is decreasing because the frequency was slightly negative. We can, in fact, plot this. So you see that this looks like a staircase of some sort, especially if I plot just a few of them, or maybe like this, because the phase integer is just integer values. Then we also have the fractional part. So this is going to be a number between minus 2 pi and 2 pi. And if we plot this on its own, it's difficult to get any sense of these numbers, but what needs to be done is to add them together, like here. So I'm going to plot the two together, and you can see that the fractional part is just a correction that can be applied to the phase integer, but it's important, otherwise we wouldn't get any good precision from this method. So, all right, we have our phase measurements, and I think that plotting the phase measurements, all of them, is not very instructive because, well, basically the slope of the phase corresponds to the frequency, but we really want to get that slope to do some kind of time derivative. And to do so, we need to decide some Doppler measurement interval or Doppler averaging interval, in this case 10 seconds. And what we will do is to subtract measurements which are 10 seconds apart. And since we have 10 measurements per second, that means we are subtracting measurements which are 100 samples apart. To do so, basically, I have my measurement rate, which is 10 measurements per second, and then 10 times 10 times 10 equals 100 samples. And I skip, so this notation is for skip, so I take the phase every 100 numbers. And since I want to be extremely precise with this calculation, I treat the integer part and the fractional part separately. So I take the differences, I'm differentiating the integer part and differentiating the fractional part. Taking differences is a linear operator, so you can do this and add the results together. And that's what I'm doing. I convert everything to float. Float is 64-bit floating points, so they have more precision than these 32-bit floating points. I'm remembering that the phase fractional part is in radians, so I need to divide by 2 pi. And I also need to remember that I have applied a frequency offset of 7 kilohertz. So this was here, we shifted everything 7 kilohertz in frequency. We need to shift it up, which by now is as simple as adding this frequency offset. And then the frequency is the phase difference divided by the time elapsed between measurements, which is 10 seconds. And I also make myself a vector of times, which is just this A range 0, 1, 2, 3 multiplied by 10. If I update this, we can see it looks like this. So initially the frequency starts close to 7,000 because the PLL block will start close to 0, and we have this 7 kilohertz offset, and then it will lock to the frequency of the signal, and it will follow it. So this was the beginning of the Doppler curve, and we have run the simulation for 10,000 seconds pretty much. So this is the Doppler curve for Vega, but we are measuring this from the signal, from the noisy signal. How to interpret these results properly and to check the accuracy of our measurement. In this kind of plot, it is difficult to see any noise in the measurements because of the scale. So the noise might be a fraction of a hertz, but the scale is a few kilohertz. So what we can do is to take a time selection. I can even take it to 10,000. So I want to avoid the beginning because we have this part in which the PLL hasn't locked yet, but I can start at 10,000 seconds and then continue until 10,000 seconds, which is past the beginning, past the end, sorry. And then this is the Doppler frequency. This is basically just the same plot minus the first 100 seconds. And then what I can do is, this looks very much like a smooth curve, like a polynomial. Maybe it's a quadratic polynomial, or maybe it has some higher order terms. So what we can do is to fit a polynomial, and we can choose the degree to something suitable for what we are analyzing. And we do this polynomial fit and then subtract the results. So in here I do a polynomial fit of degree 3. This is NumPy polyfit, so very simple. I evaluate the polynomial and subtract the fit from my frequency measurements. And if I evaluate this, I find that there is still some residual frequency, because for this long time span, degree 3 was not good enough, but I can try a degree 4. And now this is quite good. And you can see this is the frequency in hertz. So the noise we have in here is about 5 or 10 millihertz. So just to recap, we have this signal, which is 30 dB CN0. So definitely not extremely strong, but not extremely weak, sorry, but not too strong either. I would be inclined to say this is a somewhat weak signal. And then by using this PLL, as long as we can get the PLL to lock, with this 10-second measurement interval, we can get an accuracy in the frequency measurement, which is 5 millihertz, which is amazing. And if you increase the time resolution here, increase the integration time to 100 seconds, then we can repeat this, and we can see that now the error has decreased even more, because we are averaging more. So we only have one measurement every 100 seconds, but the error is maybe 1 millihertz. And now we can see that there is some higher order term. So maybe doing a degree 5 polynomial fit would be better. And yeah, the noise seems to be below 1 millihertz, maybe half a millihertz. And by the way, this is one of the ways in which deep space satellites are tracked. So by computing the Doppler in this way, we receive the signal, we run a PLL, we do these calculations. We can get the velocity of the spacecraft with great resolution. So you can convert this to velocity again, and it's on the order of millimeters per second if this was an X band and 8.4 gigahertz signal. So we are able to know from spacecraft very, very far away, because certainly this 30 dB hertz is less than what many deep space satellites achieve on a ground station. We are able to measure their velocity with a precision of less than a millimeter per second. And using that, we are able to find the orbit of the spacecraft and so on and so forth. Okay, this is pretty much what I had for today. So